Okay, good morning, everyone. I am Rayelin Alca, the Director for Projects and Administration of the Foundation for Economic Freedom, or FEF, which is the public advocacy organization dedicated to advancing the cause of economic and political liberty, good governance, secure and well-defined property rights, market-oriented reforms, and consumer protection. I'm also a member of the Technology for Property Rights project team. I will be your moderator for today to cover for Angela, who is currently on another webinar session to present on another FEF advocacy on forestry. So we welcome all of you to the second part of the webinar series, Do's and Drones, with the title Knowing is Half the Battle, which will feature studies on drones conducted by the UP Training Center for Applied Geodesy and Photogrammetry with the Foundation for Economic Freedom. This webinar series is meant to disseminate information on the use of drones for mapping, surveying, and securing property rights. The first part of the webinar series, entitled Getting Somewhere Now Without Being There, was held last June 18. It introduced drones to us, or rather unmanned aerial vehicles or UAVs, getting familiar with its components, its various types, specifications, and other features. We were also able to know of its various applications, particularly to surveying, where it may be used for orthophoto mapping, cadastral surveys, topographic surveys, agricultural monitoring, and other types of surveys. The benefits and limitations of the use of drones were also discussed. We are very thankful for our previous speakers, namely Engineer Louie Balicanta and Geographer V. Rivera, for their very informative presentations last time. And today we bring Engineer Louie back with us, and this time with Engineer Severino Domingo Jr. as the second speaker. So our first speaker is Engineer Louie P. Balicanta. He is the chair of the UP Department of Geodetic Engineering and the director of the UP Training Center for Applied Geodesy and Photogrammetry. He is also a land surveying practitioner, faculty, instructor, researcher, and now a licensed drone pilot. His various research projects are in collaboration with several universities, national government agencies, local government units, and non-government organizations such as the Foundation for Economic Freedom. His presentation today will include basic principles of UAS photogrammetry, UAS mapping process, and a short discussion of the research of UPTCAGP-LMB and FEF on the applicability of UAS for land surveys. Our second speaker, Severino Domingo Jr., is a UP graduate, licensed geodetic engineer, and also a licensed drone pilot. He has worked on several researches with the UPTCAGP, covering acquisition and processing of geospatial information from land, bathymetry, and aerial surveys. The most recent endeavors that he's been involved with are the research on the establishment of calibration baselines with the Land Management Bureau and the study on the comparison of consumer drones for property surveying with FEF. So for this webinar, Engineer Domingo will be presenting the results of a study on the accuracy of consumer drones for property surveying. So I'm sure all of you are quite excited to hear more of these topics from our speakers. So I will now turn over the floor to Engineer Louie for the first presentation. He will also discuss a bit about why the title, why the title is Knowing is Half the Battle. Sir Louie.
Thank you, Ma'am Rhea. So I will be sharing my PowerPoint presentation. Okay. So good morning to everyone. Thank you for coming to this second webinar related to do's and drones. The title is Knowing is Half the Battle. For those who are batang 80s, you are familiar with this. Since you're watching afternoon cartoons like G.I. Joe's, it seems cool to use this as a title for our topic today, since we will be discussing about concepts and processes of UAS, and we will be discussing about the outputs of our two researches with FEF. So basically, this will give an idea how the technology works, no? And then what are the recent local researches that we have done in support of proving that this drone can be used to highly technical applications and highly accurate applications, like for example, property survey. So knowing is half the battle, since you will be knowing some of the major concepts in UAS application. Okay. So this is the outline of my presentation. I will be discussing briefly, very briefly, the topics of webinar 1, and then go directly to the principles of UAS photogrammetry. Some of the mapping processes involved in UAS mapping. And then I will be discussing about the first research with LMB and FEF. And then I will turn over the floor to June for him to discuss about the drone comparison research that we did with, again, FEF. Okay, so in webinar 1, we've discussed about geographer V, Ma'am V, no? Discussed about the difference between UAV and UAS. So basically, UAV is the vehicle, no? The platform wherein we put the sensors. The UAS is more of a complete set, no? Of components, including the following. No, we have the positioning system, no, the control station, the links, no, and then very important is the payload or the sensors, no. And then she discussed about the different classifications of drones based on the for example, different drone types, be fixed wing or rotor type, or in terms of sizes, in terms of the range, no, that a certain drone can reach, and then in terms of operating time. So these were discussed comprehensively by Ma'am V last webinar 1. After which, I discussed several applications. These are some of the outputs that came out of the surveys that we've done. The first is orthophoto mapping. Basically advantageous if we want to map corridor areas or small narrow topography. Drones are very applicable for that. Topographic mapping, wherein we produce DEMs and DSMs, which are used also to produce more conventional way of representing topographic data like contour maps. Okay, and then we have this agriculture monitoring. What was provided was an output of my research advices, I think last year, no, Ms. Baxa and Ms. Martorillas, with regards to monitoring the health of the or monitoring the nutrients, no, the content of the fertilizers onto a certain plant. For example, in this case, this is a rice field, no. And then on the upper portion, we have the parcel mapping or cadastral surveying, wherein the idea is to use drones as a tool so that the outputs can be used to delineate the boundaries of a property. So we did this research, and I will discuss it a little bit more in detail later on. This research is with FEF and LMB, and also the geodetic engineers of the Philippines. And finally, I've discussed some benefits and limitations. So similar to other technology, other equipment, you know, drones has its limitations. It has several benefits, but it has its limitations. Okay, moving forward. Okay, so we'll discuss the first basic principle of US photogrammetry, which is the so-called structure from motion. Okay. Traditional photogrammetry, if some of you may remember, is quite different from what we have right now. Previously, when we use, for example, large planes containing these optical cameras, okay, the plane is allowed to be tilted at certain degrees only, no. So it must be relatively stable enough so that the images that will be produced is almost orthogonal. Okay? And then we produce stereo pair so that we can have, for example, uh, definition or information on depth, or we will, so that we can produce 3D outputs or 3D information. The current technology that is used in a drone, no, in UAS, is not limited by this. This is due to the so-called structure from motion, or what we call multi-view stereopsis. The idea is that we will be having multiple and overlapping photographs, and this will be used as input to provide feature extraction and three-dimensional reconstruction algorithms. Okay. So with structure from motion, okay, uh, the technology allows us to simultaneously and redundantly and iteratively do bundle adjustments, okay, and extract, no, information and put it in a certain database. With this, multiple images wherein a certain point or a certain feature can be found, no, with these several images, we produce no, very accurate point matching, okay, between photographs, okay, and produce point cloud, which is later used for uh, the generation of DSM and DEM. So this is the main technology used, okay, in processing, no, in processing images that we obtain from small, lightweight UAS up to the larger ones. Okay, next. I've enumerated here major mapping processes involved with the use of UAS. The first one is ground sampling distance. Then we have flight planning, block adjustment, and orthomosaicing, digitization, my most favorite step, and quality assessment. So the first one is ground sampling distance. Okay, so ground sampling distance, or GSD, is very important, okay, in our drone or UAS process, since this is an indicator of the accuracy of the map that we will be producing. Okay? As per our references, it is defined as the distance between the center points of each sample taken off the ground or the pixels in a digital photo. Okay? But for example, when we measure this GSD, actual GSD, we usually use the edges of the pixel, no? So it is more discernible to use the edges of the pixel. So I will be stopping the share and opening up another software so that I can provide a sample for you on how we can measure GST on an output orthophoto. Okay, so I will be opening a data. Okay, can you see the image? Okay, can someone? Okay. Uh, Fellow panelists, can you confirm if you can see the image?
Yes, sir.
Yes,
Visible
sir.
po yung
Okay,
image.
thank you. So this is an output of the first research with FEF. This is in Norsagaray, Bulacan. Okay, this is a flat terrain area. So for example, if I zoom to one of the points, okay, one of the checkpoints or validation point that we use, okay, I will zoom into that portion. I will use the commands. I think it's here. Okay. So this is a marker. I think this is around 15 centimeters in diameter, 10 to 15 centimeters in diameter. So if I zoom in a little bit more, okay, so you will see the pixels already. And then if we measure the distance, okay, from this edge up to this edge of the pixel, and then you look at the lower left, no? So we can see that's around 1.8 centimeter pixel, 1.8 centimeter in dimension, no? In size. So this is the GSD. This is the output GSD out of the processing. So going back to our slide. Okay. So this is the basic principle in computing or relating GSD with the sensor parameters or specifications. So the basic parameters here include the flying height, the focal length of the camera, okay, the width and length, or in this figure, length is substituted by height. So basically, this is the dimension of the image that will be produced, no, in terms of pixel numbers, no. Um, and then this is different depending on the sensor. So different sensors have different specifications. Obviously, how we relate GSD with flying height differs from one sensor to another based on this equation. So I have here an example, okay, using this drone shown in the figure. Okay, provided here in the left are the uh, image specifications or camera and image specifications. Okay, provided to us by the equipment, no, when we buy it, and then we have the flying height of 80 meters. 80 meters. So this is the image width, this is the image height. So that the values that we will put there in the equation is this 5472 and 3648 pixels. Okay, this is the flying height. The focal length is around 8.8 millimeters. The sensor height is around 8 millimeters. Okay, and then the sensor width is around 13.2 millimeters. So with this, these are provided to you. Probably the unknown thing here is the GSD. The flying height is provided to us. So using the equation, we can solve. No, we can solve for the GSD. No, and then you will be using the GSD. Okay, you will be using the GSD, which is the higher one, higher value, in computing, in providing the parameter for your actual flight. Okay. Provided that the lower portion of the slide is the web link, no, the website wherein you can have online computations of the ground sampling distance. Okay, and so other than, for example, when we go back to this GSD, okay, probably another question that can pop up at in your mind is that, how do I determine, for example, the appropriate flying height so that I can achieve a certain level of accuracy or ground sampling distance? So you just have to tweak, no? You just have to tweak and reorder the equation so that the unknown variable will be the flying height. So ano lang to, basic algebra, no? You put the other parameters at the left side so that the flight will be isolated. Okay. The next major process is flight planning. So actually, it's a standard process to us surveyors that when you go to the field, before going to the battle, actually, is for you to know the site first. No, you have to plan your activities. No, so in flight planning, you consider, for example, how many flight lines do you need to achieve the output that you need, the drone that you will be using, specifically not just the camera sensor specification, but also the type of drone that you will be using. A lightweight drone cannot be used for windy, for example, windy areas. So you will be using a much more sturdier drone. No? Terrain, okay, since we have flat terrain and then sloping terrain, the image that we will be producing also has an effect if the terrain is flat or rolling. So we must consider that in our flight planning activity. And also the availability of launching and landing sites. No? So quadcopter drones are much more applicable if the launching and landing sites are more limited. We can use, for example, fixed wings if the area has open spaces, lots of open spaces. We can also use VTOL for dual purpose, for open spaces or very challenging sites. No? But we know that VTOL is quite expensive right now. Okay, the next important thing with regards to flight planning is the overlap. Okay, overlap is important since, as we have said, we follow this structure from motion principle. We need more images to cover areas and have multiple images visualize or show a certain point, no, that can be recognized by our processing software. Okay, so this is very important, no, for us to acquire good quality images. Okay. Traditional photogrammetry only requires us around 50 to 60% forward lap, and I think around 25 to 35% side lap, if I'm not mistaken. So the number of images, for example, using the traditional equipment is the number of samples or the number of images may be less compared to, for example, what we have right now. So we will be having small images, but so many images around for a certain terrain, for example, or certain area. We may need small area. We may need around 500 images or more. Okay, since the preferred overlaps, no, is around 70% to 80%. Okay. Okay, so this is just a visualization of the forward overlap and lateral overlap. No? So the forward overlap is along the direction of the flight. It's the overlap between the two images along the direction of the flight. And then the side lap or the lateral overlap is the overlap between images of different flight lines. So here in the figure, this is the lateral overlap. So most drone, a flight planning software, like for example, this is I think drone deploy, okay, you can actually easily, no, set the side lap and front lap, and you will know how many flight lines that you will be producing and how many number of minutes, for example, you need to complete the flight. So I remember when our college days, no, we are doing this manually, but with the softwares that we have right now, okay, we can do this on site. Now, before the actual flight, you can do your actual flight planning on site because it's very easy using the software. Okay, the next major activity is block adjustment and orthomosaicing. So the idea of this process is that we want to connect the images. So we have so many images, no? So we will be producing these mosaics, no? We're trying to connect them and also provide real-world positioning on these images. So the idea here is that we will be using several ground control points. That's one option. Okay, and then second one, if your drone has these image stationing coordinates capability, meaning it has RTK or PPK accurate positions or equipment on the drone so that we can have these positions, we can use this. Okay, so the idea is that you input in the software the coordinates, the calibration coordinates, no, of the GCPs, or the coordinates of the GCPs used for calibration, no. So typical to a photogrammetric process, no, we usually use two sets of data, the calibration and validation data. So we cannot use the calibration points to do validations, since that will produce an accurate result, since we use those points for calibration. So there's a separate set of points used for validation. Okay. So at the end of the day, we want to produce, okay, an accurate image, orthomosaic image out of the control points that we produce. And I think based on the researches that we have done, okay, you usually do this using several iterations. It's not just one-time processing, since you want to provide a good combination of calibration points in terms of position, in terms of geographic positions, I mean, no, so that you can have more accurate results. So it's not just one-time processing, but probably you will need to do at least twice or even thrice. Okay. So, okay, so after this, so this is actually quite tedious. So for a small sample, we may need to do processing let's say 2 to 4 hours of processing, and then you will have to wait, no. Larger areas will need longer time. So one of the probably limitation of this kind of activity is the hardware capability of your processing computers, no. It should be very high. Okay, the next step is digitization. So this is my favorite part. Okay, so I asked June and V to process the image, and then I will be doing the digitization. So this is the most enjoyable part of this activity, since the idea here is for you to just be able to see on the image the marker that you have put on the ground. So the left side of the slide, you can see the photo of the marker that we've used in the study area. So we simulate the dimension of a mohon, no, or a property survey monument, no, and then it must be seen when you zoom in. It must be seen on the orthophoto that you produced. Okay, so this is the same sample that I've shown you earlier using the Global Mapper software. Okay, so after that, you may use now certain GIS software, no, to digitize, okay, to digitize or vectorize the points. So either you digitize it by using a point entity, and then you click on the center of this marker, and that is the position of the boundary, for example. Or maybe you can use polyline or line entity to connect the lines delineating the boundary of the property. So in terms of practice, I think I much prefer the point entity, and then later on I can just connect this using CAD software, no, or a GIS software. Okay, this is the most important part, okay, so that we can say that the results of our mapping activity and digitization is accurate. So quality assessment. So based on the technical bulletin provided by LMB, they adopted these equations in assessing the accuracy of our map, orthophoto map, and then the digitized boundary corners. Okay, so the first equation is just a simple RMSE along the X and Y axis, and then the combined RMSE. And then the latter two equation is the accuracy used to evaluate the position that we produced out of our digitization. So the idea is that based on, for example, okay, the difference between the 2 points, for example, two coordinates describing 1 point should be less than 10 centimeters. So based on my interpretation, this RMSEX, for example, multiplied by 2.4477 should be less than or equal to 10 centimeters. Okay, these are sample outputs of the RMSE computation in the population study area. No? So for example, the RMSE here is around, total RMSE is around 4.6 centimeters along the X and 3.2 centimeters along the Y. And then the checkpoints, no? When you use the checkpoints, it's around 5 centimeters. Okay. So this should be evaluated. And if we found out that the computed RMSE for the checkpoints is high, no? The standard deviation or the RMSE is very high, we may have to choose other GCPs as a possible calibration point, no? And then we use another processing for that, and then we produce these images, and then we assess again the checkpoints if it's less or higher than the first iteration. Now this is the accuracy assessment of the digitized points. So we provided simulated boundary corners on the area, and then we try to compute this, no? Compute this RMSE. So to do this, you may have to provide a separate set of coordinates for these points. So you may use RTK GPS, for example, or total station survey to generate these checkpoints, no? And compare this with the positions that you've obtained from the images that you digitized. Okay, I think this is the last few slides. So if you have questions, just raise it later. So in 2017, okay, the Foundation for Economic Freedom, the UPTCAGP, DNR, GEP, and Mr. Volkman, the one at the back of me. So I'm at the center, no? The tall one is Mr. Volkman. I think he is the also the consultant of FEF with regards to this endeavor. So they did an earlier activity, an earlier experiments in somewhere in Cebu, if I remember it right. No? So we did this experiments in Norsagaray, Bulacan, way back in around March, I think, of 2017. Okay, 3 sites were used representing a flat terrain. So this is the flat terrain area in the image, in the picture, and then rolling terrain and highly urbanized and rolling terrain. This is the methodology that we used to perform. So we try to investigate also how is orthophoto mosaicing using the more traditional use of GCPs on the ground. You have multiple GCPs, and orthophoto mosaicing using the image positions out of the PPK capable drone. Okay, so we try to compare this also, no? And then it has 3 major steps nga, as you can see here in the slides, from data acquisition to data processing and data analysis. Probably Voltaire will discuss the more industry method, industry related method. This is the research methodology, but Volts will explain what you can, the method that you can use for the practice, no? Later on, I think in the 3rd or 4th, I think the 4th webinar. So please look forward to that webinar also. Okay. So these are some pictures summarizing the activities that we did. I'd like to recognize that the drone that we used during those times is a UX5 drone lent to us by SciTech. No, it has a launching pad, no, and it has a capability. We use other drones also. For example, we used EB from Rainbow, and I think Volz also brought his Phantom 3 during that time. So if you can see here in the slide, no, at the left side of the slide, we also recovered reference point. This is BLLM number 4 of the Cadastral Survey of Norsagaray, Bulacan. So in short, similar to the traditional method, for us to relate old surveys and new surveys, we must use the reference points used in that previous old survey so that we can have a link or a transformation between the new method and then the old system. Okay. At the second image from the left, you can see that we use GPS to do the ground control survey. And then at the rightmost image, no, we see that we also use GPS to do validation and calibration point survey to determine an independent coordinate for the points, since this is a research study. Okay, so these are the sites. These are sample outputs. So this is the population area. Okay, overlaid onto it is the cadastral map that we obtained from DNR. Okay, this is the first one is in Poblacion. The second one here is in Tigbe. So this is I think this is a housing project. So we did a survey on that area. Okay, again, the cadastral lots, no, were overlaid onto the processed image. And then we have here the highly urbanized rolling terrain site, which is in Barangay FVR. So we are challenged, for example, in this site, since, for example, our validation calibration points, we have to repeat again. The first one, we try to do RTK survey or PPK survey, but the output that we produce is not that accurate. Make sure that your calibration validation point must be more accurate than what you are trying to assess or measure. So when we go back, we use rapid static survey. Since there are many obstructions here, many building structures, many high wire tension lines or power lines that has an effect on GPS. Okay. This is the last slide. Okay. This is the same area as I've shown you in the previous slide. This is Tigbe, no? I'd like to recognize that the problems, for example, that we are facing as a practitioner in surveying still exist, even if we use drones, no? You use UAS. So for example, at the left side, we use the coordinates out of the control points. But as you can see at the right side of the boundary, no? And it's not very fit. When you zoom in, it does not fit, no? Based on the survey accuracy requirement that we have. Okay, the second and then the third images shown here, okay, we use the common point. So we were able to recover the mohon, describing the boundary of the property at these portions of the lot, no? So as you can see, okay, it is you can actually move it. So for example, this is GIS or your CAD. You can still translate it accordingly. And then at the rightmost side, which is very off, no, when we use the coordinates based from BLLM number 4, this is the output. No? So basically, what I'm saying here is that, okay, the existing problems that we have right now, like coordinate system, common point, still exist. But the advantage here is now we can visualize, no, and show to for example, certain entities, okay, the situation, and maybe later on we can find some solutions out of this, sound decisions out of this. So it's very hard for us to explain to our client that there's an overlap, there's a gap, if we use our traditional uh, line maps lang, no? Line maps, so without a background image. So this is one advantage of having a secondary data like the orthophoto when we submit this to DNR for approval, no? Okay. So in summary, okay, we were able to use the methodology. This is not original from us, no? It was tested in previous researches in other countries, but I think this is the first local research that was initiated not just by one single entity like UPTCAGP, but of course FEF, which is the one, no, who really is the proponent on this, no, and then LMB was there and GEP was there. So it's a good collaboration between different stakeholders in surveying. Accuracy assessment was done and was shown that the outputs can achieve the required accuracy stated in our current policies and our current survey guidelines. And finally, okay, out of this activity, additional policies and guidelines were provided. I think Engineer John Domingo will later on discuss this more in detail. Now, this LMC number 2017-003 and LMB Technical Bulletin number 2 series of 2017. Okay, and then I'd like to thank FEF for doing IECs on this, different IECs, not just this webinar, but trainings as well, so that the use of drone can be much more appreciated by the different practitioners. Okay, so with that, thank you. And I'd like to turn over the virtual floor to Engineer Domingo.
Okay. So thank you, Sir Balicanta. I hope you're all having a good morning, and I hope most of you, if not all, are still all ears to this webinar. This will be a bit technical, and there will be a lot of tables and numbers in this presentation. But should you have any questions, we can entertain them later and respond to them to the best of our team's knowledge. So as shared earlier by Engineer Balicanta, a research was conducted in 2017 regarding drones for property surveying. Out of the research, 2 related policies on the use of drones for land survey were drafted and approved by the LMB and was made effective on January 2018. However, questions have been raised on the usability of all types and models of drones for the purpose of property delineation. Some surveying practitioners thought that only highly expensive drones are the only drones that can achieve the level of accuracy needed for the purpose of property surveying. If this is true, then the proposed technology is very exclusive, since only large surveying companies will be capable of acquiring such tools. To address this, a second research was conducted in 2019, and this aimed to assess the applicability of various drone brands and models available in the Philippine market for the purpose of property surveying. So it had 3 main objectives. The first was to document the available UAS in the Philippine market. The second was to select a representative for the different UAV types and evaluate their performance and output with the help of local distributors. And finally, to present the applied testing methodology and the results of the analysis of the outputs. So in the Philippines, drones are categorized according to weight. So based on CAAP's civil aviation regulations, small remotely piloted aircrafts, or RPAs, are drones with a gross weight below 7 kilograms, while large RPAs are those with a gross weight of 7 kilograms and above. We currently don't have a standard definition for the term low-cost drones, but according to the Penn State Department of Geography, low-cost drones, also referred to as consumer-grade drones, are close-range models with prices of up to 500,000 pesos. These units usually have an operational range of about 5 kilometers and flying endurance of 20 to 45 minutes. Despite the presence of drones specifically designed or reconfigured for mapping purposes, low-cost drones nowadays are equipped with GNSS capabilities and inertial measurement units, making drones capable of conducting and completing automated surveys following the predetermined flight plans uploaded pre-flight. So consumer-grade drones are either equipped with fixed imaging devices or cameras or are built to accommodate external sensors. So the processing of UAS data, specifically the images, typically follow a three-stage process. So this begins with the creation of a project specifying the images, camera model, the coordinate system, and the solution template to use. And key points are extracted from the images, and the adjusted 3D coordinates and attitude angles at each image station are computed. This forms an adjusted block of images using the measured coordinates of the image stations. This initial processing generates a sparse point cloud, and then GCPs and checkpoints are then measured, and the solution is recomputed to improve the georeferencing of the block model. It is during this stage that the adjustment solution is assessed, including the accuracy of the block adjustment in terms of RMSE using both GCPs and checkpoints. Then the next stage is the densification of the point cloud, which finally allows us to generate products such as digital surface models, elevation models, and orthomosaics. So the accuracy assessment is carried out as part of the initial processing of the images. If GCPs are utilized in the processing, the georeferencing accuracy of the block is measured using the RMSE of the block adjustment. Accuracy is then computed by multiplying 2.4477 to the RMSE value. These are the other imperative equations that were used in our study to assess the accuracy of the outputs. So we have the distance formula, the angle formula, the core distance, and we used area by coordinates. So the main documents followed by geodetic engineers practicing land surveying in the Philippines are the DAO 2007-29 and its implementing rules and regulations provided in the DANR Memorandum Circular 2010-13. So the allowable position of error for isolated survey, specifically for relocation or verification survey, shall not exceed plus or minus 10 cm. In terms of area, the allowable difference shall not exceed 1 square meter for every hectare. So the study site is located in the southeast area of the UP Diliman campus. It has an approximate area of 14.5 hectares and covers parts of the National Science Complex, the Sampaguita Residence Hall, the UP Integrated School, the Diliman Learning Resources Center, and the College of Home Economics. So 8 GCPs were distributed within the defined 14.5 hectares. 4 out of the 8 GCPs, one on each corner of the study site, were set as calibration points, while with which the ortho images were georeferenced. The remaining GCPs served as checkpoints and were situated within the delineated study site as well. The GCPs were established through 30-minute rapid static observations connected to MMA 39. So MMA 39 is a first order NAMRIA reference point located within the compound of the UP campus along the University Avenue. So PRS 92 Zone 3 coordinates derived from the control surveys were used both for georeferencing and for comparison of position values with the UAS acquired data. The coordinates of the simulated lot corners were derived using a 5-minute PPK observation, referring to the points to the GCP Station 6, whose coordinates were computed from the static survey. So tarpaulin markers were used as photo controls. 3 marker designs were prepared for various purposes. A 1x1 meter design for the calibration and checkpoints, and 10 cm and 15 cm diameter design for the simulated lot corners. Prior to the actual flights, these markers were laid out on the GCPs, and markers were also placed on the simulated lot corners. For drones with post-processed or real-time kinematic capabilities, GNSS-based setup was also done prior to actual drone flight. So the images gathered through the UAS surveys were mainly processed using Pix4D Mapper. A second workstation was also used to check for the consistency of the processing, and PRS-92 coordinates of the calibration points were integrated for georeferencing purposes. Through the software, orthophoto mosaics were generated. In both systems, the output coordinate system was set to PRS-92 Zone 3. And both computer systems were also set to utilize all of their resources in processing the images. So stations 1 to 4, located in the extents of the project, were used to calibrate the positioning of the output. When marking the GCPs in the image, the theoretical error S values were kept to a maximum of 1 cm horizontally and 2 cm vertically. So the orthophoto mosaics were loaded and analyzed using third-party GIS software. Validation and quality assessment of horizontal position values using checkpoints were done using the same GIS software and Microsoft Excel. Due to the proprietary software needed to process the RTK and PPK data of some of the units, the GNSS processing for those UAVs was performed by the respective operators from each participating supplier and was submitted to the researchers for the processing of the images. So the research team coordinated with drone suppliers and distributors in the Philippines and invited them to participate in the experiments. 5 models were made available and selected to represent their respective price ranges and sensor capabilities. Entries were categorized into small and large UAVs as per CAAP regulations, and low cost, mid-range, and high-end units based on the market prices of each unit. High-end models include PPK and RTK capable UAS. I would like to apologize because for now we cannot disclose the specific brands and models that participated in the research, as we do not wish to send a message that only these drones may be used for GE's purpose. The study would rather concentrate on researching if drones from different tiers would be capable of providing the necessary output and the accuracy. So this table summarizes the camera sensor details and shooting modes used by the respective UAVs. All the flight plans of the respective UAVs, excluding that of Drone C, targeted a GSD of better than 2 cm per pixel. Drone C targeted a GSD of 4 cm per pixel, but according to the operator of the unit, the flight planning software they used overcompensates its estimates and actually produces lower GSD values after processing. So the images were first processed using the provided horizontal positions of the systems. So drone A, B, and C utilized their RTK and PPK capabilities, and the GNSS positions were processed by the respective operators due to the proprietary access to their software. So this just means that we process the images without doing manual georeferencing with the GCPs. These tables summarize the horizontal offsets and direction between the static observed coordinates of the GCPs and the digitized coordinates from the automatically georeferenced images. Considering the distance and direction values of the observed offset between the digitized points and their GNSS computed positions, excluding the use of manual georeferencing shows that there is a difference between the two processes that includes scale and rotation. It may be inferred that in order to obtain better position accuracy, GCPs must still be integrated in the survey and processing of UAS imagery, even with RTK or PPK capable UAVs. All images were processed using the same processing options in Pix4D Mapper. The table on the upper left shows the summary of the Pix4D processing results from manually georeferenced images. So this means that we used to manually georeference images with the GCPs that were observed on the study side. And this includes the output GSD, the computed RMSE from the manual georeferencing, the overall processed area coverage, and the number of images used. The table on the upper right shows the summary of accuracy of the output based on the RMSE values from Pix4D Mapper's processing report, where 4 GCPs were used for calibration. So the Pix4D Mapper processing software outputs its own accuracy report or RMSE values. And then the table on the lower right shows the summary of the computed RMSE values of each process as found in the difference and coordinates between the static observed points and the digitized points from the respective ortho images. So the RMSE and accuracy values were computed in 3 solutions, namely using all 8 GCPs, using only 4 calibration points, and only 4 checkpoints. So this part was manually computed and was not did not rely on the processing Pix4D Mapper software. And on the lower left shows the processed ortho image of the respective UAVs. So this is the output from the drone A. This is from drone B. This one is from drone C. You can see that although all the drones targeted to fly over the same target area, the output of the images, the processed output images seem larger than other images from the other drones. And this is from drone D, and this is from drone E. So the following figures show the before and after digitization attempt for the simulated lot corner. So after processing the images, we try to zoom in to where the simulated lot corners were located, and we try to digitize the simulated lot corners. So this is from drone A, and this is from drone B. Identification of lot corner markers with 10 cm diameter was only possible on the images from drone B with an estimated GSD of 1.09 cm per pixel. Although all the photo control markers could be identified from all the processed ortho images, out of the 5 tested units, only the ortho image output from drone B, D, and E were usable for the lot corner marker identification. In these 3 ortho images, the lot corner markers were confidently identified on the images. So the results from the digitization of corner points from ortho images obtained using the sensors of drone B and drone E with dot corner position accuracies of 7.4 cm and 3.4 cm respectively are within the requirement specified in the LMC 2017-3 and the LMB Technical Bulletin number 2, wherein the accuracy must be less than or equal to 10 cm. Similar computations were done with the digitized lot corners from drone D. However, its accuracy of 13.7 cm did not meet the accuracy requirement. The distance formula and the angle formula were used to compute for the distance and bearings of the meets and bounds of the simulated lot parcel as shown in the PPK-derived technical description on the left. So the same equations were used to compute for the distance and bearing from the coordinates derived from the different UAS. The deviation column is the assumed monument movement using the chord formula, where it considers the distance value as the radius and the bearing difference value as the angle. Note that each line is independently used to solve for the movement value. For drone B, for the drone B image-derived technical description, the greatest difference in distance is in the line 2 to 3 with a difference of 1.6 cm, while the greatest difference in bearing is in the line 7 to 8 with a difference of 7 minutes and 45 seconds. And the largest expected deviation is 2.8 cm. So for drone D, the greatest difference in distance is in the line 10 to 1 with a difference of 1.5 cm, while the greatest difference in bearing is also in the line 10 to 1 with a difference of 18 minutes and 27 seconds. And the largest expected deviation is 3.2 cm. For drone E, the greatest difference in distance is in the line 1 to 2 with a difference of 2.2 cm, while the greatest difference in bearing is in the line 10:1 with a difference of 14 minutes and 26 seconds. And the largest expected deviation is 2.5 cm. The least independent possible movement from all the monuments is 1 millimeter, while the greatest independent possible movement from all the monuments is 3.2 cm. Considering the allowable position of error for an isolated survey, specifically for relocation or verification survey, all the UAS-derived simulated lot parcels pass this requirement. So the area of the simulated parcel was computed using the area by coordinate method, considering the required maximum error of 1 square meter per hectare. The allowable difference in area for the 65.744 square meters is 0.007 square meters. So none of the UAS-derived lots pass this requirement. However, since the convention for the notation of the area of the lots is rounded to the nearest integer, rounding the calculated areas of the respective UAS-derived lots, all of them pass this requirement as well. So the research aimed to assess the applicability of various drone brands and models available in the market. Around 5 models were tested, and 3 of which are considered as high-end UAVs, namely Drone A, Drone B, and Drone C. So Drone D, which is considered as a mid-range UAV, and Drone E, which is considered as a low-end UAV. Other models were not tested due to time constraints and non-availability of the suppliers on the schedules provided. So the overall computed accuracy of the produced ortho images based on Pix4D Mapper's processing report were all within the 10 cm accuracy limit. Drone C being the most accurate at 1.5 cm expected accuracy, and Drone D at the other end of the spectrum with an expected accuracy of 5.9 cm. However, based on the checkpoints accuracy, Drone E topped the list with an accuracy of 4.2 cm, and Drone D at the bottom with 8.8 cm. From the 5 units tested, 4 of the units were able to operate and survey the target area with a resulting ortho image GST within 1 to 2 cm per pixel. So with Drone B being able to produce the lowest GSD of 1.09 cm per pixel, while Drone A producing the highest within the 2 cm pixel per limit. 2 cm per pixel limit with a GSD of 1.88 cm per pixel. Drone C, although it was claimed that its flight planning software overcompensates its GSD estimate, its final GSD value of 3.2 cm per pixel went past the 2 cm per pixel limit. So in relation to the output GSD of the units, only the ortho image results of Drone B and Drone E were successful in terms of lot corner marker identification and fulfilling the accuracy requirement for property surveying as prescribed in the LMC 2017-3 and the LMB Technical Bulletin number 2. Although the lot corner markers were somehow identifiable from the ortho image from Drone D, its computed lot corner accuracy of 13.7 cm did not meet the required standards. It is important to note that although Drone A has the same camera sensor as Drone E, the resulting GSD of Drone A reached 1.88 cm per pixel, while Drone E reached 1.63 cm per pixel. This may be attributed to the 10-meter difference in the set flying height of their respective flight plans, with the 0.25 cm difference in GSD, and with a value still below the standard 2 cm per pixel. It was not possible to identify the center of the lot corner markers from Drone A ortho image. The effect of the flying height is also predominant between Drone B and Drone C, with both their onboard camera sensors packing 42 megapixels. And since Drone C flew at a significantly higher altitude of 200 meters above takeoff than Drone B at only 80 meters above takeoff, Drone B produced a significantly more detailed ortho image with a GSD of 1.09 cm per pixel. The Philippine Surveyor's Manual prescribed a 10 cm limit in terms of position for isolated surveys, such as relocation and verification surveys. This requirement was achieved by the output of Drone B, D, and E, with a maximum independent monument deviation of 3.2 cm. However, the manual's requirement of limiting the error in land area to 1 square meter per 1 hectare was observed to be unachievable if the maximum positional error is 10 cm. The allowable difference in area for the 65.744 square meters simulated lot is 0.007 square meters. The digitized parcels from drone B, drone D, and drone E ortho images resulted in a zero point 0.2 square meter, a 0.18 square meter, and a 0.029 square meter difference respectively. However, if we consider the convention of rounding the area to the nearest whole number, this qualifies the output of the 3 UAS for the requirement. So based on the results, it can be said that low-end UAVs such as Drone E with its 20 megapixel camera sensor may be applicable for property surveying along with the likes of high-end UAVs such as that of Drone B. It is important to note that even high-end UAVs such as Drone C have their operational limitations. Flight parameters such as flying height above takeoff should always be taken into consideration when preparing your flight plans. The clear advantage of higher-end UAVs with regard to property surveying is their capability of covering a larger area with detailed results such as that of Drone B. So Drone B covered the same target area as Drone E, but accomplished it with one 14-minute flight and produced a GSD, an ortho image with a GSD of 1.09 cm per pixel, while Drone E needed 4 15-minute flights to cover the same area and produced a 1.63 cm per pixel ortho image. While it is true that a lower GSD value reflects significantly on how identifiable features are on the ground, having a GSD of less than 2 cm per pixel does not necessarily guarantee an output that may pass the accuracy standards. Overall, the research was able to show that low-end UAVs may be used for property surveys. And with that said, it is still important to learn how to operate these tools regardless of their classification. Acknowledging the pros and cons of these instruments can be used to leverage a geodetic engineer's surveying advantage. And that ends my presentation. Thank you for listening.
Thank you very much, Engineer Louie Balicanta and Engineer Jun Domingo for the very interesting and very informative presentations. So, since medyo nagmamadali na tayo, no? It's already 11:23, so we won't be able to answer all your questions. So, I will just pick out some of the questions here and then just pass it on to the one who can answer the question. So, the first one, what are the best weather conditions when flying a drone or a UAV?
Okay. Morning. Daylight, probably 10 to 12. And then, this is based on our first research, Ma'am Rhea, no?
Yeah.
I think when we are at the site, we see that, for example, between 10 to 12 and then 12 to 2, it's good because, for example, the shadow is not that bad. No? So it's quite different for let's say, solar observation. It's 8 to 10 and then 2 to 4. It's, for drone, it's, I think, 10 to 12, 12 to 2. June, you may add.
Yes, I think we have to look for, we have to monitor the shadows because the processing software may have problems when there are large shadows within the image, especially when we try to survey during the times when the sun is moving very fast and the shadows change. Since we have to have pictures overlapping each other, we have to have at least the same scene for every picture.
Thank you. So the second question, sirs, can you expound further on the principles of structure from motion? Why is it possible for us to extract 3D information from UAS images using SFM? Sir Louie.
Jun, you want to explain or I will explain? Ako na lang. I think that you can add, no? Pero the simplest way of explaining this is, for example, you have a figure and then you take a pictures of this and then you have control points on a certain figure, let's say a base, no? Or a head of a person. And then you use the control points to try to connect to extend or something the points so that it can fit on the figure. So you're trying to two-dimensional images and try to recreate the three-dimension aspect of the figure. After doing that, doon na in-extract yung DSM and then DEM when you were able to reconstruct the 3D model. Is that, Jun, can you add?
I think it also has to do with the concept of the stereo pairs. So you have to have the image overlaps, and then with stereo pairs, we could identify the 3D features from the flat images.
Okay, thank you. So it was mentioned that in order to generate better orthomosaics, 70 to 80% overlap is usually preferred. What would be the basis for that?
Oh, I think the basic idea is that you need to see certain points at multiple images. We can only have that kind of situation if you have so many images, no, that has this 0.1 on it, no. So if you have less than 80% or 70%, there's a large chance that you cannot get that point on a certain, let's say, image number 1. So the idea is that with 80% overlap, you can see at several images 1 point, a certain point. John, can you add?
I'd also like to add that it basically needs more photos because for the generation of the orthomosaics, the software just selects from the pool of photos that you have. So having a 70 to 80 meter overlap would provide you with more plumb photos or orthometric photos of certain features, and it would also decrease the distortion from the edges of the images.
Okay, so another question is that one of the challenges in applying UAS for 3D mapping is on urbanized areas, is the manifestation of relief displacements in individual images. So while the ortho rectification process can minimize or eliminate this problem, what would be the best strategy to implement during flight planning or image acquisition stage such that this problem will be minimized? The usual approach is to fly higher, but the GSD will be sacrificed. What would be other potential solutions?
Jun, you can answer that using our Lance Mode 1.
Yes.
Okay.
So another potential solution would be to use a double grid flight plan. So if for example, you have your first flight plan that runs from south to east, then you have another overlapping flight plan that would run the flight plans from north to south. So it would at least the camera would have the ability or would be able to capture all the usually 4 faces of a 3D object. It would be able to capture the 4 faces of your structure.
So 2 flights, huh? You 2 flights with 2 different directions, right?
Yes.
Okay, another one here. Based on the presentation, quality assessment seems to be the last stage of the UAS mapping process. So how do we ensure during the earlier stages that we would be able to pass the quality assessment? Because it would be very costly now if the QA failed.
Yes, it depends on the drone that you have. If you can you can have a larger area or smaller area. That's one. Second is GSD. So
Yes.
that's why you have to compute GSD.
2 centimeter better or better.
Yes, or better. So that's one good indicator. If you can achieve that, let's say 70% of your output may be good, no? But that's just a number, no? What I said about, for example, the large the area or the smaller the area. If you have, for example, a large project, no? So each day you have to process your data immediately, no? Since it will consume so many hours of processing, you don't do the processing after completing only the data gathering at the end of your project or at the end of that stage. So you must do processing at the onset that you have the data.
Yeah.
And then GSD is the clue.
Yes, that's why we encourage to use 2 centimeters or better.
Yes. I think 2 centimeters or better. It's not just for accuracy, but as June mentioned in his presentation, this is a clue wherein we can see the actual point on the image clearly. If we cannot see the entity, the object on the image, we cannot delineate it correctly. So our objective is not met.
Okay. So, merong question on the open source software that can be used. Yes, QGIS software can be used.
For the digitization.
Yes, for the digitization, because
Ah.
there are other softwares needed for processing other data. Is drone surveying already accepted to be used for surveying by DNR?
Based on the technical bulletin, ma'am,
Yeah,
saka
we
memorandum
already
circular,
have,
yes.
we have already the memorandum circular, LMB memorandum circular number 2017-003, adopting the alternative use of UAS, commonly known as drones, in conducting land surveys. And meron din sila ng technical bulletin number 2 series of 2017. That's the technical guidelines complementing the LMC. So with regards to the implementation, I think that would be parang regional basis then.
I think, Ma'am Rhea, you missed one question before that. Yung
Mm-hmm.
how do you deal with
Okay,
overlapping lots?
overlapping lots. Okay.
So similar to what I've explained in one of the slide, no, these are problems still existing even if we use drones. But with the image that we produce, we can now visualize and show to DNR or show to the client, no, that if you overlay, for example, the boundary of your property, this is the overlap, no. If you overlay, for example, the actual location of the property versus the one from the documents, you can see now the actual situation and show to the client, no, the actual situation and find a solution basically. But it will not solve the overlapping problem. It can lead to solving the problem.
Yeah. Okay. So regarding the different UAVs used in the comparison research, do you think that the result would be the same for all UAVs if the camera used have the same parameters? Sample, focal length, same sensor dimension? June?
Sorry?
Um, would the result be the same daw if the cameras used have the same parameters? Focal
Yes.
Oh,
length.
well, it actually depends on, for example, for the
Kasi like for example,
it,
may mga 20 megapixels. There are 3 drones used in this study na 20 MP.
yes.
Did they
Yes,
do
I
all
think
this?
pwede, kaya lang nga, yung ano naman, dito naman papasok yung drone type na gagamitin mo, no? Kasi yung tamang velocity, maybe applicable, fast velocity can be used for fixed wing, a slower velocity for a quadcopter type. So other than GSD, other than the sensor specification, the drone specification also plays a part in providing comparable or accurate results. Tama ba, Jun?
Yes, sir. And also the performance should also be visible to the, for example, for you, the buyer. I think that some of the issues that we have is, although the products have the same specifications, the performance of each product may differ even with those same specifications.
Is it of great difference, Jun, or minimal difference?
Uh, it depends, sir.
Okay, sige.
Okay.
Okay.
So we cannot really say na pare-pareho siya.
Yes.
Yes.
Okay. Regarding the comparison research, still, did the project design and flight planning stages strictly consider the required accuracy? For example, flying heights and GSD set appropriately such that expected products will be within the desired accuracy. Yeah. Di ba? Nag-set
Yes.
tayo ng 2 centimeter below na GSD.
Yes. So for the actual flights, the licensed drone pilots from the respective suppliers were the ones who operated the units. We did instruct them to limit their flight plans to obtain orthophotos with 1 to 2 cm per pixel, or 1 to 2 cm per pixel or better. It's just that one supplier was confident that even though their software was reporting something higher, that it would produce it would still be able to achieve the required accuracy.
So
Acquired
yun
GST.
yung nag-fly ng 200 meters, no?
Yes, yes.
Can you clarify daw the price range threshold on how to consider UAV as low cost, mid-range, and high end?
Um,
Nandun eh.
Yes, as for now in the Philippines, I don't think we have standard for defining this. So we just based our tier classification based on the Penn State
And states.
literature that we were able to gather.
Okay, so in your own opinion, is UAV already is can UAV be used as standard for property surveys?
Yes. I think so, yes. No, so we have proven it, for example, with these two researches. And then some practitioners are also using UAS already. I think, Ma'am Rhea, may napa-approve na tayong plano, di ba? That used
Yeah,
UAS,
in region 13, yes.
Region 13. So it was actually tested already and evaluated by DNR.
Yeah,
No,
but
that
Sir
is,
Louie, we have to clarify also that in the course of doing the drone surveys, meron pa rin tayong, parang it complements the other surveying instruments as well, di ba?
yes, tama-tama. So parang ganun din, minsan common sense, no? You will not use drone if you want to survey 1 hectare land lang, no?
Mhm.
Composed of 4 points, no? So if you can use a total station, so much the better. But if that 1 hectare land is located somewhere that is not accessible to you, probably you can use also drone. So it depends on the situation and then the availability of the technology and then syempre the
Economics,
budget of the project, no?
economics, yeah, the
Yes.
economics of it. So may I ask what the allowable RMSE is?
RMSE, if you multiply it by 2.4477, less than 10 centimeters, so that's around 2.8 centimeters. Around
Yun yung
2.8 centimeters. Yung RMSE.
ang allow.
RMSE, well, kasi it should be less than 10 centimeters, di ba, Ma'am Rhea?
Mhm.
So 2.4477 times 2.8 is roughly less than or equal to 10 centimeters.
Okay.
So,
Okay, so yun.
so
Yun
parang
yung
ganun,
allowance.
around
I think
2.8.
it's around 4 cm.
4 ba?
Yes,
2.4?
4.
Ayun, sorry.
So if you divide 10 by 2.4477,
Okay.
it's around 4
Sorry.
cm.
Okay.
4 cm pala.
Okay. Thank you for that, Balls. I am using a Phantom for RTK drone. When using it in RTK mode, it is also logs.obs file that I believe can be used for PPK processing. What software can be used for this kind of processing? PPK processing daw, software. What can be
Okay.
used? Usually
Okay.
kasi parang ano yan, no? Nasa, ano yan, proprietary?
Proprietary yan eh. So, parang for example, for our purpose, yung ating mga partner distributors na nag-process nung PPK and then binigay sa atin yung parang file
Processed.
that corresponds
Yes.
to the position. Parang ganun eh.
Okay.
So, it's another good venue for another research, no? Kasi hindi pa natin, kumbaga we are just black box pa sa atin yun eh. We rely on the supplier to
Yeah.
provide us with that.
Yes po. So ito nga yung question niya. Would there be one software for all to process all data? Iba-iba yung pinanggalingan ng data. One software for all. For example, for the drones. Kasi meron din tayong part ng, di ba, nag-establish ng control. So merong processing of data, GNSS data. Pero if for processing ng drone images, we use yung, di ba, Pix40 or the other one. And then we use QGIS for the digitization.
So, iwahiwalay pa talaga. No?
Yeah, and then pag gagawa ng survey plan, baka ilipat pa sa sa AutoCAD. Yeah. So, yun yung tanong niya kung merong one software.
So far, wala pa.
We should develop one.
Yeah.
What software is best to use for processing drone images? So, dalawa yung nagamit ninyo, di ba, June? Or have you also used an open source?
So far, only Agisoft and Pix4D.
Yeah.
Medyo mas user-friendly kasi sila. And yun po yung may access kami ngayon sa department.
Pero wala pa sa open source. I know that there are available.
Meron yata open
Meron
source.
sa open source pero hindi pa lang po siya ganun ka user-friendly.
Okay.
Parang yung iba kailangan pang may may line of codes ka pang gagawin.
Okay. So we have the last question. The comparison of 5 drones were made in relatively flat terrain. Will the accuracy variation change if these drones were tested in a rolling terrain?
It would, yes, it would definitely change the accuracy. Kasi lalo na po yung sa ating GST value. So the GST value is usually just estimated throughout the surface of your survey area. So if we have, although, for example, it reports a good GST value for a flat terrain, for parts where it's either higher or lower, it could have a higher value GST in that area, and possibly could also affect the ability to be able to identify the features for those areas.
Okay. Thank you so much, Sir Louie, Sir June, Engineer June, and Engineer Volts as well for answering the questions from our attendees. So thank you very much for participating in the second part of our webinar series, Do's and Drones. Hope to see you all again next time. To end this webinar, we would like to thank our partners, the UP Department of Geodetic Engineering, UPTCAGP, the Asia Foundation, and Atlas Network. So bye.